Coming back, everyone. So in the last part, we're going to look at how to break the circuit size barrier for secure computation. Just to recap a little bit, so far we've seen a lot of different techniques for getting different kinds of MPC. So broadly categorized into the constant round approaches based on garbled circuits, and the linear secret sharing style approaches, which could be based on preprocessing, multiplication triples, or FSS, as Alette was talking about, and these silent preprocessing gadgets or pseudo-random correlation generators to generate this preprocessing. But even with all of these fancy gadgets, if we look at the overall communication cost of these protocols for general purpose circuits, we still don't have anything better than linear in the number of gates in the circuit. And with the garbled circuits side, we additionally have this factor lambda overhead, at least in the security parameter. Of course, the nice thing about many of these things is they're very lightweight in terms of the types of cryptography they use. They're pretty efficient and practical, but they need a lot of interaction from the parties. So we'd like to see how to avoid that. And I'm going to start by exploring a few of the different tools we have as cryptographers for solving this problem and give a little bit of an overview of the history to start off with. So in the beginning, there was fully homomorphic encryption. Actually, only since 2009, but yeah. And FHE is the kind of standard approach to getting MPC with communication independent of the circuit size. It basically solves this problem as good as you can possibly imagine, but it's also kind of a heavy tool. It's not efficient for very complex computations, and it's nice to explore alternative approaches. Okay, and then after FHE, so we've already seen a lot about this correlated randomness approach for one-time truth tables, which gets you information theoretic security in the preprocessing model. And this can in fact be used to bypass this circuit size barrier in some cases, as we'll see shortly. But what I'm going to focus on in most of this talk, hopefully if we get time, is something called homomorphic secret sharing. Perhaps I'm a little bit biased here because this is something I've been working quite a bit on the last few years. And of course, the other areas also have a lot of other papers I haven't mentioned on here and are very important. But HSS, I think, offers kind of something unique in the different kinds of techniques it gives you, and opening up pathways to get sublinear secure computation under different assumptions. And so we look here at the different communication complexities you get from these approaches. You see that FHE is still by a long way, the only way we know to get communication completely independent of the circuit. So most of these approaches we're getting a log factor, maybe even just a log factor saving in the circuit size, which you might think it doesn't look that impressive. Like, why are all these people working so hard to get such a tiny shaving off the circuit size? But I hope that when you come to see the techniques, you see that there's some really beautiful ideas here going on, and some of the technique can be valuable in other areas. And hopefully, if enough of you get together and work on these problems over the summer, we might be able to even beat some of these barriers. Okay, so let's start where it all began, fully homomorphic encryption. The concept of which was actually first invented by Rivest, Edelman, and Dertouzos in a paper from 1978, where they envisaged this possible tool where you can take an encryption of a message X, represented by X in the blue box here, and then perform some kind of homomorphic operation on the encrypted space on the ciphertext to get a valid encryption of the results without learning any information about what's inside. And then upon decryption, using the secret key, you learn the function applied to the plaintext. Of course, there is some kind of non-triviality requirement we have here that this decryption or the evaluated ciphertext itself should be independent of the function that we're being evaluated to rule out kind of trivial solutions where you just append the function to the input ciphertext. Okay, but it was, I guess around 30 years before Gentry managed to figure out how to realize this and build fully homomorphic encryption based on lattices. Okay, so once we have FHE, it's pretty straightforward to build a standard 2PC protocol with sublinear communication. Alice will generate a public key pair for the fully homomorphic encryption scheme, send over the public key and her encrypted input, and then Bob will be the evaluator and homomorphically evaluate the function in the encrypted domain, obtaining the encrypted result, and send this back to Alice. Alice can, of course, decrypt and get the result. So there's a slight catch here in that we require some circuit privacy property of the FHE scheme to be able to do this safely, but that's not too hard to achieve in general. And this is for two parties. Also mention that this can be extended to the multi-party setting using a threshold FHE. And there's many lines of work that optimize and improve threshold FHE so that the distributed key generation and decryption processes get better efficiency for, say, a large number of parties or better parameters for the underlying schemes. Okay, so how does FHE look? Well, Gentry's first scheme was based on ideal lattices, and it kind of introduced some somewhat non-standard assumptions and was pretty technical. And then over the years, this was progressively refined, and we now have kind of two subsequent generations of FHE schemes that are used fairly commonly today. The second generation followed this BGV style approach based on learning with errors, or the ring learning with errors assumption. And in practice, it's particularly nice if you use ring LWE because it supports this kind of batched SIMD style homomorphic evaluation where you can have the vector encryptions of plaintext and operate on them all in parallel to get pretty good amortized efficiency. Whereas the third generation is not so good in the batch setting, but if you just want to do a kind of single execution, the nice thing is that it has this pretty efficient bootstrapping algorithm, which is bootstrapping is an essential part of any fully homomorphic encryption scheme on these slides, where you have to do this homomorphic decryption operation inside FHE to be able to reduce the noise level in these noisy ciphertexts from working with learning with errors. So I'm not going to get into the technical details of these schemes. That's all I'll say about these for now. But this is just a kind of overall picture of the space. I'll mention a couple of interesting open theoretical questions in FHE. So, of course, it would be great to have FHE without relying on lattice assumptions. There's a little asterisk here, and that, yes, now we have I/O, and we can, in principle, build FHE using I/O. So we have this on different assumptions that are not LWE, but this is like kind of a very long-winded, roundabout, and complex way of getting FHE. Even something, getting a more direct construction under the same assumptions as we have to build I/O would itself be interesting, or even better, diversifying and finding new assumptions. There is a couple of recent papers which make some progress in this domain. So there's a paper from Eurocrypt this year, which relies on linearly homomorphic encryption from DDH and the sparse learning parity with noise assumption to get a kind of low degree, somewhat homomorphic encryption scheme. And there's also another paper exploring the possibility of building homomorphic encryption from code-based assumptions, which has also been done in the past to some limited extent. And you can get a little bit there in terms of also low degree homomorphism, but it's also not quite as good security guarantees as what you really want. You can only give out, I think, a constant number of ciphertexts before the security breaks down. And secondly, a long-standing open problem now since 2011 or so is to build FHE from learning with errors for unbounded computations without relying on a circular security assumption. As far as I know, this is still open and seems to be very hard. Okay, so moving on to unconditional security. So what can we do in the preprocessing model to find another way of breaking this circuit size barrier? So we've seen a lot now, these one-time truth table protocol with a permuted shuffled truth table generated by a dealer in the preprocessing phase who will secret share and distribute this truth table among the parties to get us this very nice online communication efficient, simple information theoretic protocol in the preprocessing model, of course with exponential storage. And there's one small tweak to this protocol, which I described in the first talk, where instead of being a kind of standalone 2PC protocol, you can actually make this be a more generic protocol that works on secret shared inputs. So it takes secret shared inputs X from the parties, and then you run the protocol, and you get secret shared evaluation of the truth table applied to X. This requires a similar kind of preprocessing material, basically shares of the truth table shifted by these random masks R and S that every possible evaluation in the input domain. This protocol again has this nice kind of one-round structure. Okay, so here now I guess the input space is n bits instead of 2 n bits. So now it's n. Yeah. It just the x is just a general n bit string, secret shared. So yeah. Okay, and once we have this secret shared protocol, the nice thing is we can use this as a building block in a larger protocol for more general circuits. And the idea is very simple, but it wasn't until 2019 that Couture published this paper that presented this, where you take an arbitrary Boolean circuit, which has a kind of nice enough layered structure, where I can divide it into layers, where each layer has depth d, which is log in the circuit size, and is layered such that the kind of the outputs of one layer always feed directly into the input wires of the next layer, so you don't have any kind of jumps going from wires that skip several layers. Okay, so if we have this depth d chunk of a circuit or layer of a circuit, then this means if we look at each output wire within this layer, then this is a relatively low locality function, right? It's depth d, so there's at most 2 to the d different inputs on the previous layer that this output depends on, which means the size of the truth table that computes any one of these output bits is at most 2 to the 2 to the d, which is linear in the circuit size. So all we care about here really is it being polynomial in the security parameter. So it's something efficient. Okay, so now we can just evaluate this circuit using our secret shared one-time truth table protocol in a kind of layer-by-layer fashion. And if you play around with things in the right way, then you can make it so that you can kind of batch all of these truth table evaluations in the same layer, and you only need to communicate O of W bits for one layer, where W is the width of this layer. So then this gives you a total communication. If your layers are kind of evenly distributed enough, you get this total S over log S number of bits to evaluate the entire circuit. And the storage cost for this, of course, is one truth table for each of these gates we have in the circuit, which is essentially quadratic in the circuit size. So it's not great, but it's polynomial. And overall, we have communication sublinear in the circuit size. Okay, so one interesting open question I think I'll mention now is that we still don't know of any way of getting anything similar to this for circuits without having this layered structure. Yeah? Sorry?
So you expect maybe to have some lower bound. Other such?
Some lower bound on with preprocessing?
So upper bound, a low bound in communication with something.
I think lower bounds on communication for information theoretic MPC are kind of difficult. There are some lower bounds, but they're usually not very strong or in very limited models. Yeah.
For like generic transformations of circuits into, I think you can do some like massaging to put sort of arbitrary circuits into these kinds of layered structures. The overhead of that kind of defeat the savings you get from doing that.
So I'm not really familiar with these transformations, but I would expect for a general circuit, it's probably gonna kill your savings here.
It's a factor of the depth. You pay the factor of the depth, which is much bigger than log.
Okay. So yeah, that's basically all that's known in the unconditional setting. We get this log saving, which is nice, but maybe there are other ways to do better. Who knows? So now what if we don't want to rely on FHE, and we also don't want to rely on this preprocessing model? What can we do? So enter homomorphic secret sharing, which you can think of as kind of the little brother of fully morphed encryption, where now instead of a single server who is evaluating encrypted operations on ciphertexts, we have a distributed version where we have two servers who each performing their own evaluation algorithm. And initially, the inputs are fed into some sharing algorithm and split into two shares. these shares might not be, linear secret shares. They might be something more computational. There might be some, any kind of special shares. We just need to be able to evaluate on them and end up with some evaluated share such that if we sum these things together, then we get the output of the function we want to evaluate. Okay, so the basic properties of HSS are the standard security property of secret sharing that the shares each individually hide the input X. Similar to FHE, we want some kind of succinctness properties so that the shares are compact even after evaluation. And finally, we want correctness such that after reconstructing, we get the correct output of the program. I know that this is quite a strong requirement that we just have addition in the output here. You can also relax this to more general reconstruction functions, but in this talk I'm going to be focusing on addition, and that's also nice for certain use cases, but it's not always essential. Okay, so just as a quick warm-up, okay, if you have additive secret sharing, of course, additive secret sharing is linear, so now you can just evaluate linear functions on additive shares, and you get HSS for any linear function. Okay, very straightforward. Second warm-up, if we want Shamir sharing in the multi-party setting, so now n parties instead of two parties in some honest majority setting, then you could again exploit this nice multiplicative property of Shamir sharing, where let's say if we have two secrets X and Y that are Shamir shared, the parties can pointwise multiply their secrets to do some kind of homomorphic multiplication in the eval procedure. And then after doing this, if you multiply by the Lagrange reconstruction coefficients, lambda1 up to lambda n, then you end up with exactly an additive secret share of the result X times Y. So generalizing this in the natural way, you can get an information theoretic honest majority HSS for evaluating degree D polynomials with up to T corruptions, where as the degree grows, you need the number of parties to be at least D times T plus 1. So this can be good for low degree polynomials, but doesn't really scale so well. Okay, so in general, HSS, I guess, is usually framed as this distributed analog of fully homomorphic encryption, so where you're relaxing the security requirement to two or more non-colluding servers. But HSS has also seen a lot of other applications since it was first started to be investigated. So it can be used to build advanced forms of private information retrieval. Worst case to average case reductions have been derived using HSS. You can build advanced cryptographic primitives like trapdoor hash functions, pseudo-random correlation generators and functions, which Alette mentioned in the previous talk. And very recently, there's works building constrained PRFs and even privately puncturable PRFs from HSS-style techniques. So this is not always kind of black box using HSS, but using the kinds of techniques that were developed have turned out to be pretty powerful. Okay, so this might look slightly familiar from Alette's talk, but now instead of PCGs, we're talking about HSS. There is a similar landscape to the different kinds of assumptions and worlds we have. So the top end, based on LWE or FHE style assumptions, you can also get HSS for arbitrary circuits. You can get HSS for branching programs or NC1 circuits using a slightly simpler construction that doesn't require all the machinery of FHE. And then going a step down, what I'm going to be focusing on today is these cryptomania, but without FHE assumptions, so DDH or the DCR assumption used in Palier encryption, which can get you certain kinds of HSS for branching programs with different characteristics. And at the bottom, there's also these slightly less expressive families of HSS, such as the Lapland regime using learning parity with noise, which gets you HSS for certain types of low degree polynomials. And then minicrypt using just one wave functions, you get these, I guess, FSS style point function HSS schemes, basically, where the point functions, HSS and FSS are kind of the same. Okay, so let's jump into this landscape of the DDH-based constructions to start with. And I'm going to show you this high-level template from the breakthrough paper of Boyle, Gilboa, and Ishai from 2016, getting HSS for branching programs. So what's a branching program? Well, you don't really need to know what a branching program is. except that in this talk, we're going to view a slightly different model of them, which is just a circuit. It's an arithmetic circuit with addition and multiplication gates, where each multiplication gate is restricted to be always between at least one input wire and then maybe some other intermediate value of the computation. So here in the green boxes on the slide, I'll always represent the input wires, and then the other orange box here is some intermediate wire y. Okay, and this is powerful enough to capture any log depth computation and even log space computations. So in the constructions that we'll be looking at, so they deal with these different kinds of wires in different ways. So for each input wire in particular, the parties will always get, as part of their shares, some encryption of the input X under some linearly homomorphic encryption scheme, say Elgamal. Okay, and then for the intermediate values, we often refer to these as memory values, which are just intermediate values in the computation. And the invariant that you maintain throughout the computation is that these will always be shared in some linear secret sharing way. Not necessarily strictly additive secret sharing, but just some linear sharing. And then with that, to get our evaluation of the circuit, we just need ways to carry out these operations. So firstly, additions on inputs and memory values. Thanks to the linear homomorphism of the encryption and the secret sharing, this is easy. And then multiplication between inputs and memory values, which is where all the hard work goes. And then finally, output. Okay, we have linear shares of the outputs once we get to the end. So then this gives us our reconstruction procedure, which is just addition. Okay, so before getting into multiplication, I just want to give a quick maybe recap or reminder for some of you of how with Elgamal we can do a very simple two-party distributed decryption procedure. So imagine a setup where we don't ever multiply two input values. Yeah. So we have an Elgamal public key, so group element G, and then G to the power D, where D is the secret key. And let's say we have some setup where this is secret shared across the parties with additive secret sharing into D0 and D1. And Alice and Bob have some common ciphertext encrypting a value X. And they want to decrypt this into, let's say, into some kind of shares or in some distributed manner. Okay, so what I'm going to do is, let's say Alice will compute this value G0, which is the first element C1 in the ciphertext divided by C0 to the power of her share D0. Then Bob will compute C0 to the power of his share D1. And if we divide these two group elements together, then these are, I guess I say multiplicative, they're actually kind of divisive shares of the original encryption of X, which is this value G to the X with X in the exponent. So if you go through the math here, this is kind of like doing a distributed Elgamal decryption, where we get this ratio of the results gives us the share. Okay. So far, so good. So let's look at this blueprint for HSS multiplication, which kind of holds for used in several different schemes in the literature. So for each multiplication gate, the parties both have an encryption of the input wire X, and then they have these shares of the intermediate value Y in some linear shared form. Okay, and in step one, we're going to do this Elgamal distributed decryption. But to do it, we're actually going to require that this sharing, this linear sharing we have, includes not just additive shares of Y, but also additive shares of Y times by the secret key, D, used in Elgamal. Okay, and once we do that, we can basically use the shares of D times Y in the previous distributed decryption step, where now instead of D, we use D times Y, and also the shares of Y, and we can end up getting these multiplicative shares of G to the X times Y. So this isn't exactly what I showed on the previous slide, but a small tweak to that. You can probably figure it out in a minute or so. Will get you exactly this ratio. And the second step is to run what I call DD-log, or distributed discrete logarithms, which think of it for now as a magic box, which converts this multiplicative sharing into additive sharing of the integers. Okay, if we do this, we're done.
I'm confused. Where did the dy come from? Where did d come from?
So D is the Algorithmic secret key. But let's just assume we have this as a setup.
I thought you were assuming everything is secret shared in an additive way. Now you're saying no, the secret sharing is not just additive, but there's also some d.
I mean, it is a linear secret sharing, right? It's additive plus an extra linear part.
For example, do we need a d prime for the result?
Yeah, so that's coming.
Oh,
Okay, so what I have here, it doesn't get you, the correct output format compared with what you started with, right? So what you actually do is you need to end up with shares of d times x times y, so you can continue. And to do this, you essentially run the same step, but now use an encryption of d times x instead of an encryption of x. And then you can get these shares of d times x, y.
the same d?
The same d. So then you have a potentially circular security issue, but yeah, there are ways to work around that. There's a few thorny details that I'm brushing under the carpet, but that's the high-level idea. Yeah. So basically, if we have a way of doing this DD-log algorithm, then we can get our HSS for branching programs by running this procedure. Okay. Okay, so how does it work? How do we do distributed discrete log? So we're working in a group G. Let's say I had an order n and generate a little g. And after running this first part of distributed decryption, parties have these multiplicative shares, G0 and G1, which give us some g to the power z for our plaintext z. So I'm going to put these on a kind of number line containing all the group elements, starting with Alice's share G0 and incrementing by powers of g up until we get to G0 times g to the n minus 1. And somewhere along this line, we also have Bob's share G1. Now, if we look at the distance between these two shares, of course, this is going to give us the plaintext z. What we want is a way to compute the shares of this plaintext z without interaction. So as a first attempt, let's say Alice and Bob agree upon some kind of arbitrary, maybe random distinguished element h in the group and compute the distance between the input shares G0 and G1 and h. Okay. If they could do this, then okay, these are now subtractive shares of the input z, right? Z0 minus Z1 gives us z. Of course, the problem is they can't compute this, right? Doing this in general is just solving a discrete logarithm problem. We don't know how to do that in an arbitrary group. So we're going to relax this a little bit. Instead of having a single distinguished element h, suppose Alice and Bob somehow out of band managed to agree upon a sparse, maybe pseudo-random set S of multiple distinguished points distributed evenly across the whole group. And then I will just take my share G0 or G1 and then try to find the closest distinguished point I can by repeatedly multiplying with powers of g. And if Alice and Bob both do this, then hopefully they will both hit the same distinguished point. And if they do that, then they get their subtractive shares of the input z. Of course, the problem now is we have multiple distinguished points. It could happen that one falls kind of in between the two parties' shares, and then they hit different points, and we have a correctness error. So now there is basically a trade-off here. By kind of tweaking the sparsity of these distinguished points, which are used in the algorithm, if we make them more sparse, then of course we have a lower chance of error, but then we get a larger computation, and vice versa. If we want to make the computation faster, the error will blow up. So the annoying thing about this is that despite many optimizations to this blueprint over a few years, there's basically no way of getting rid of this 1 over polynomial failure probability. And a second side effect of this is it also, of course, limits us to small message spaces because we need that these two input shares, G0, G1 of Alice and Bob, can't be too far apart. And in fact, there was a paper from Crypto 2018 which showed that if you want to solve this problem, then you basically can't do any better than this 1 over poly failure probability from this line of papers. without solving some variant of discrete log with a small exponent assumption. Yeah?
This inverse poly, is this a correctness error and a security error, or just a correctness?
So it's just a correctness error, but you also kind of have to be careful because sometimes the presence of a correctness error might reveal something about, it might depend on the inputs. But the nice thing is you can make it at least kind of arbitrarily small, as long as it's still 1 over poly, by just blowing up the computation by some poly factor. Okay, so that's basically the state of affairs for DDH. It looks like this is pretty hard, but maybe we can do better. Now, don't be put off when you see papers claiming lower bounds, claiming this is a hard problem. There's often ways around this, and this is where Pallier comes in. So Pallier encryption does not use DDH groups. It uses, I guess, related to RSA groups. We have an RSA modulus n, but we're working modulo n squared. There's one of the basic facts about this group is if we take the element 1 plus n, then this is kind of special. 1 plus n raised to the power x. If you expand it, you get 1 plus x times n, mod n squared. So discrete log is actually easy with respect to this base 1 plus n. So even though in the whole group, discrete log is probably hard in the Pallier group, it has this subgroup of order n where discrete log is easy. Okay, so now if we try to apply Pallier encryption to this framework, then Pallier is a linear homomorphic encryption scheme. Turns out you can do exactly the same kind of distributed decryption trick where if you have shares with the secret key, the parties can locally get these multiplicative shares, G0 and G1, such that the ratio of these two things is now 1 plus n raised to the power of the message which you originally started with. Okay, so now the fact that we've mapped this ratio into this easy discrete log subgroup is kind of bringing hopes that maybe this doesn't have to be so hard to solve, right? It could be there's ways around this lower bound. Okay, so let's look at the same picture as before, but now mapped into the Pallier group, where we have G0 and we increment by powers of 1 plus n, so we get to G1. And okay, as a starting point, let's say, okay, we have a single distinguished point H, just as before. If the parties can compute the distance to this element, then they can compute their additive share of Z. But because discrete log is easy, now you can do this by taking your input and taking H divided by your input, which will always fall into this discrete log subgroup where discrete log is easy. You can actually, in polynomial time, compute this discrete logarithm. So this looks like it becomes kind of trivial for Pallier, right? There is just one catch here, which is, okay, we have to agree upon this element H. So before this space was the entire group of a prime order DDH group. But now Pallier, the group is not prime order, right? This is actually not the entire group. This is a coset with respect to 1 plus n, starting at G0 or the other share G1. So it only contains n elements out of the full size close to n squared group. So if we can agree upon the same element H somehow, then we're done. Okay, so for the next step, I guess another basic fact about Pallier is that this group Zn squared, the multiplicative subgroup, can be broken up into this direct product of the additive group Zn and the multiplicative group Zn star. And we're going to use this by taking Alice and Bob's private inputs, G0, G1. So we can write G1 as G0 times 1 plus n to the power of the message, right? And remember, our goal is to find some group element H, which is in the same coset of these two elements. So if we we apply this isomorphism, map each of Alice and Bob's inputs, G0, G1, into some product of elements, where the left-hand side we have 1 plus n to the power of some a, and on the right-hand side we have some element of the multiplicative subgroup, which is some value b, raised to the power n, it turns out, then because these things are in the same coset, then when we do this isomorphism, of course, we always get the same kind of b on the right-hand side, because these elements only differ by some power of 1 plus n. Okay, so in particular, if we take G0 and G1 and reduce them modulo n, then okay, the 1 plus n part disappears, goes to 1, and we get b modulo n, and they get the same value. So this gives a way of Alice and Bob agreeing upon some group element, and it turns out that if you go through a few lines of math, which I'm not going to present on the slide, then yes, this element Gi mod n is also in the correct coset, and we found the right element H. Okay, so to recap, so for Palier, we can follow basically the same blueprint as the BGI-16 construction from DDH, but now we get a construction where we have negligible correctness error, and we can even support exponential size messages, arbitrary messages, or almost as big as mod n. And we have this catch where, okay, if we do things naively, then every time we multiply, we also have to do this multiplication with encryptions of the input times the secret key, and we have this possible circular security issue. But it turns out there are nice ways to avoid that by using the Damgard-Urach crypto system instead of Palier, which basically generalizes Palier to message space integers mod n to the s for some exponent s.
Is this a different assumption?
It's under DCR.
Same assumption.
Yep, same assumption. It's just a generalization and reducible to the same assumption. Yeah, so using Damgard-Urach has some nice advantages. Circular security issue goes away, and also now each input. So because with Palier, the secret key doesn't actually fit in the message space, so you kind of have a problem of encrypting the secret key. You have to break it into several chunks. This also goes away with Damgard-Urach. Okay, and there's also a public key variant of these constructions where there is one kind of challenge of setting up this whole thing where you need to generate encryptions of every input multiplied with the secret key, which seems like it might not be so easy, but there are some nice tricks to do that in a relatively simple manner without having to rely on kind of complex threshold protocols. Okay, so that's HSS for branching programs. What does this get us in terms of 2PC with succinct communication? And first, how am I doing for time? Plenty of time, right? Great. Yeah, I want to say I might be the first speaker to finish on time or even early, but let's see how it goes. Okay, so once we have HSS for branching programs, the natural thing is just to say, okay, how do we get two-party computation for branching programs? Okay, this is pretty straightforward. So as a kind of setup for the 2PC protocol, at least if we want a somewhat generic construction, then we rely on some generic two-party computation protocol to set up this public key such that we have secret shares of the secret key. And then Alice and Bob will, of course, exchange encryptions of their inputs. And on top of that, we need a way to generate encryptions of the inputs times by the secret key. But this can be done without too much effort. And then we run the HSS evaluation protocol. We have shares of the key. We have encryptions of all the right things we need. We can evaluate any restricted multiplication circuit. And we'll get shares YA and YB of the output of the circuit. And now, if we're doing the DDH version, we have this non-negligible error probability. Then, we have to kind of account for the fact that this might be incorrect. So one easy approach to do this is just to repeat this, say, lambda times. If we have constant error probability, and then take the majority of all of these outputs. But of course, to prevent this correctness error also causing some privacy error, then we need to run this majority function inside another two-party computation protocol. Okay, but then we should get the correct output, and we have a two-party computation protocol. Okay, so how does this look in terms of communication? So the input phase is going to be some polynomial in lambda. independent of the function. The input sharing phase has, of course, some multiplicative overhead in the input size proportional to the security parameter, because we're working with these Elgamal ciphertexts or Pallier ciphertexts. And then the output phase, at least for DDH, we have another poly lambda blowup caused by running this MPC protocol to output the majority. Because with Pallier, then we can at least avoid this poly lambda blowup in the output phase and directly get something only proportional to the length of the output. But it turns out also there are some nice tricks in DDH to get rid of these poly lambda factors using hybrid encryption. It's quite easy to compress the input encryptions. And furthermore, there's some tricks to compress the output encryptions to get basically rate 1 in the number of outputs. So under either DDH or Pallier, we will get the same kind of 2PC for branching programs with succinct communication. So if we want to apply this to more general circuits, then just like with the correlated randomness model at the beginning, we're going to impose some kind of nice layered structure on the circuits, where the circuit is divided into layers that are kind of sufficiently deep. And this time, we're going to look at each layer as a kind of big branching program gate. And when written as a circuit, then the depth of this will be at most, must be at most logarithmic in the circuit size. And then this means the branching program representation will have still polynomial number of gates. Okay, so it means overall, we only have to pay for the inputs and the outputs of each branching program gate. So just as previously, we had a log-log factor saving. Now here, because we can support depth log in the circuit, overall, for nice enough circuits, we get a log C saving in the overall communication complexity. Okay, so yeah, that's the main result for these two constructions. For branching programs, it's fully succinct, and for general circuits, it's slightly succinct with this log factor saving. But note that this is the order of C over log C number of bits, so there's no kind of security parameter blow up here, like garbled circuits. And yeah, there are other applications like generalized forms of PIR for more expressive forms of read and write queries, where you want to kind of evaluate some branching program when you make a query. Okay, so in the last few minutes, I'm going to talk a little bit about some possible extensions to HSS and some more recent work. And one of the first things you might be wondering is that, okay, we've seen all of this for just 2 parties. Can we go beyond 2 parties? And this is a fantastic question. It's quite difficult. There's been some limited progress in recent years, but there are also some barriers. So one kind of very negative result from a few years back at Crypto 2019, that if you look at this distributed discrete log procedure and try to imagine coming up with some kind of multi-party analog that works with more than 2 parties, then it turns out this is actually information theoretically impossible. And essentially, there is a kind of implicit component of distributed discrete log where you have additive shares of some bit, and you need to kind of convert this from one modulus to another modulus. So for instance, from integers shared mod p to integers shared mod 2. And with 2 parties, turns out this is quite easy to do. Or it kind of works at least with exponentially small failure probability. But once you extend this to multi-parties, you basically always get a constant failure probability. And that seems impossible to work around. So if we're going to design something for the multi-party setting, we need to use different techniques. There's a few results based on different assumptions and different techniques that manage to do this in some way or another. First is the line of work that mostly uses variants of LPN and sometimes other public key assumptions to get usually, I think, log-log savings in the circuit size for a constant number of parties. Secondly, there is a multi-party HSS construction from the sparse learning parity with noise assumption for any number of parties, which has some kind of annoying correctness error, but at least can still be used to get sublinear communication MPC for any number of parties. And finally, there's a more recent work we had from Eurocrypt last year on something called succinct HSS, which can be based on the same kind of public key type assumptions as the Palier construction, so DCR. You can also instantiate it using class groups, which have a similar easy discrete logarithm subgroup. And the core idea behind succinct HSS is that it gives you a way of compressing these memory shares. So these were these linear shares where you have additive shares of the secret key times by some message y, such that if you say you want to distribute a large batch of memory shares at the beginning of the program, naively this would require at least linear communication in the number of values you want to distribute. Using succinct HSS and the techniques in this paper, you can compress this and get something sublinear in the number of shares you want to distribute using basically succinct kind of Peterson hash function. And taking this doesn't directly lead to a multi-party HSS, at least not in the kind of natural definition. But if you put things together in the right way, then you can still get multi-party computation for general sufficiently wide layered circuits with complexity of number of parties times circuit size divided by log of circuit size for any polynomial number of parties. So this is kind of almost, or like up to a few caveats, matching what you get in the two-party setting from DDH or DCR. Yep. So do you mean the sublinear MPC schemes or but for general circuits or for branching programs?
Both.
Yeah, so I think if you just look at branching programs, it's not too bad. You pay roughly, at least for Palier, you maybe one exponentiation or so per gate in the Palier group. But once you want to go to the sublinear MPC results, then you have to throw on these hybrid encryption tricks and things, and then you're getting a bit non-black box, and it gets more expensive.
So it's like poly, but with a very big polynomial.
Yeah, potentially. I've not tried to calculate the polynomial, but yeah, it could be big. Yeah, there might be ways to throw in optimizations and do this better for general circuits, but I think people haven't looked too much at the general construction.
So maybe you already addressed it, sorry, but I guess you can do things pretty aggressively with LWE and like from other public key stuff. So what about information theoretically and purely symmetric key? Are there some kind of barriers in terms of doing something? You said it's like hard, but just maybe remind us what is known for information theoretic and meaningful.
Yeah, so information theoretic with correlated randomness, we have this log-log saving I mentioned at the beginning. Without correlated randomness, there's basically nothing. That's an open problem. Minicrypt, can you get the log-log saving without preprocessing in Minicrypt? No? Okay, so maybe that's also open still.
Also, like, how does this compare with FHE in terms of concrete performance? Like, FHE doesn't have this polynomial computation.
Yeah, so I think for general circuits, this is not so great. These are more feasibility results. I think for the branching programs, it's, I don't know about direct comparisons, but it's not too bad. Like, it's conceptually very simple. You just have to do, a couple of exponentiations per gate. These are quite big group operations, so they can be quite slow. Like FHE, especially if you run it in the batch regime, is probably faster. So I think it's something that's not super practical yet.
So it mostly I should view it as like theoretical feasibility.
Yeah, I think that's the bigger picture, but I think they lead to at least what I would view as kind of somewhat practical results. Like you can implement them, at least a lot of it. You could go ahead and use it. It might not be the fastest thing, but it gives you something that is kind of quite clean conceptually to understand and implement if you want, and
What
maybe
about
there's room for.
What about the application you mentioned, like PIR for branching program? Is there some application, there's some advantage of using this and like that's a generic FAG?
Yeah, I'm not sure. I think I'm not up to date with the state of the art of PIR for FHE. Okay, so one of the direction to explore is, of course, pushing the capabilities of these constructions and going beyond branching programs. So, of course, the main limitation with these programs is we have this restricted multiplication operation where every multiplier involves input wire. The dream would be to have a way of being able to multiply two input wires. Okay, but this is, at least it should be impossible to do directly, right? We have some linear secret sharing. We don't know how to multiply linear secret shares like that. But in some cases, there is some recent partial progress which shows that this can be done if you have a case where these two intermediate values, the x and y, are both known by the same pi. So you can locally multiply intermediate values by viewing these secret shares of d times x and d times y as a kind of algebraic MAC, where d is the secret MAC key. It turns out this MAC can be made to be fully homomorphic using DCR or DDH or a number of other assumptions. This gets you what I view as some kind of semi-private HSS for a more expressive class of programs. So two parties here who have inputs x and y can use this construction to succinctly compute any program of the form some arbitrary polynomial size circuit like x multiplied by some restricted multiplication or branching program circuit applied to both of the inputs x and y. So you're extending just the branching program with this ability to apply an arbitrary circuit to the same input of one party and multiply it into the output.
Can you do it on both parties, like some C prime Y multiplied as well?
Yes. I mean, you can multiply. I think maybe not, because that would be something degree 2 in the memory values.
Why is it called semi-private? What is in the semi?
Yeah, so semi-private is because this C of x part, x is known to one part. Yeah. So good. So this gets you something a little bit more than branching programs, and it turns out to actually be also somewhat powerful. So this in particular can be applied to garbled circuits. And with this very recent line of work, with a couple of papers from the end of last year and the beginning of this year, where you can get sublinear sized garbled circuits for Boolean circuits or arithmetic circuits with asymptotic complexity, saving a log-log factor in the circuit size in the number of bits, or for arithmetic circuits, the number of field elements or ring elements, which are communicated for the garbled circuit.
How does this compare with the previous OPC result? Like this has only log saving, but previously you have log saving. So it seems like this is worse.
Yes, but it's a garbled circuit, so it gets you constant rounds. The previous 2PC result is not actually constant round because you have to interact for every layer of the circuit. Yeah, so this is the first constant round 2PC with sublinear communication without relying on FHE. There's some other applications if this technique in the ILL paper can get you constrained pseudorandom functions for general polynomial size constraints. You can also get private puncturable pseudorandom functions and more. Okay, so that's just about bring me to the end. I think I'm on track for my goal of finishing on time. So I think I've already mentioned some of these open questions as we went along. So yeah, firstly, removing this layered requirement on the circuit for almost all of these constructions is a wide open problem as far as I know. Secondly, in the information theoretic setting, we only have these results using correlated randomness. So we don't know what happens if you want, say, information theoretic NPC with an honest majority with T less than n/2. Is it even possible to bypass the circuit size barrier in that setting? That's completely unknown, and there are a few lower bounds on the communication complexity of information theoretic NPC, but they're quite restricted in models or what they actually achieve. Of course, HSS beyond NC1, we have some partial progress. It would be great to see how far we can push this. You know, I have the dream of eventually getting HSS for P, so you can match what you can get with FHE, but yeah, who knows? So one of course, the most important tools underlying all of these results is this dd-log operation. So we can do dd-log with 1 over poly error from DDH. We can do it with negligible error from DCR or class groups, or even LWE. These are all kind of you know, public key style assumptions, which quite heavily limit you in either computation time or ciphertext size affecting bandwidth costs. And it's not clear to me that you even require public key assumptions to get something like this technique, right? Maybe there are other assumptions out there that can get you the same kind of result. And finally, in the multi-party setting, so we've seen that we have some results getting low degree forms of HSS for multiple parties, but right now they don't quite match exactly what you get in the two-party setting. And it would be great to see if there's a way to upgrade these two-party constructions to get multi-party HSS for exactly the same class of functions. I'm happy to take more questions.
Maybe like a global question. So for yesterday's workshop, we started with like super fascinating theoretical results, kind of similar to what is done here, and then just kind of switch to maybe start with the real world. So MPC in theory is like equally old, you know, as proofs, right? And I know there is like a huge branch of people are trying to push to reality, or maybe Lane will mention.
I'll talk about real world if you want.
So is there anything, maybe either you can say, but obviously it's like fascinating to know why is maybe MPC gets less adoptions and proofs, and what is kind of the state of the art of real world kind of impact.
I'll also talk about
Oh, you'll talk about it. Okay.
I guess I can.
From the title was not clear.
Yeah. I'm curious to hear what you have to say, but I guess I can give a quick perspective, which I think part of what's driven zero knowledge has been blockchain, right? Where it's like, you know, very natural use case. MPC also has some use cases there, but it's a little more niche. And also, I think MPC is actually really hard to just implement completely and deploy compared with something non-interactive like zero knowledge. So that is a barrier. You know, we have a lot of prototype implementations out there, mostly from academia, but none of them are that well polished. There's nowhere near as many people working on this as we have in zero knowledge. But of course, there is a lot of practical work. I think Let and I have focused a little bit on some of the more theoretical areas we're interested in, but there's also a lot of practical stuff in there with lots of advances and implementations, improving numbers every year.
Any other questions? Do you have questions?
Yeah, I have two questions. What can you say something about malicious security, and also this information theoretic? What can you explain? Like there's some lower bound paper that some kind of sublinear is not possible.
Yeah, so I'll take that one first. I think the lower bound paper I know of says that you cannot get better than a factor n times the input size in terms of total communication, which means there is a kind of factor n overhead compared with computing the function that's there. And there are examples of functions where the input size matches the circuit size, but of course that's more general, and it doesn't rule out anything completely general. There are other lower bounds which make assumptions on the protocol. For instance, protocols that operate in some gate-by-gate model. You can derive circuit size lower bounds, but quite strong. And then for malicious security, so at least on a theoretical level, all the sublinear results can be extended to be malicious security just by applying the right kind of sublinear zero-knowledge proofs. Some of these techniques also seem quite amenable to malicious security because there's not that much interaction. There's not that many places that can go wrong, but I think it hasn't been explored much as passive.
Okay, thank you so much.